So we're going to jump to part two, and my pleasure to introduce Jeremy Eder. Who knows Jeremy Eder that's already in the audience? And if not, you will after this talk. No pressure.
Appreciate it. Can y'all hear me in the back? Thank you very much. Okay. As Shaq mentioned, I'm Jeremy Eder. I work on network performance for the CTO's office at Red Hat. Today I want to take you through some network tuning that's got both latency and throughput components to it. So before I get started, can I get a sense of your workloads? Are they more throughput or latency sensitive, or do you have a mix? Latency? Throughput? Okay, and mixed, everybody. Who's using 1 gig? 1 gig, 10 gig, 40 gig? IB. A couple IBs, nice. Okay, so the first step is to make sure you have all your ducks in a row before you even get into the network tuning area. And that's where these folks come in with the automatic alignment that stuff like NuMD does. And what I have here is kind of a recipe or a checklist to get you up and running, make sure there's no unnecessary interference on the system. Things like making sure your standard build doesn't include anything, doesn't necessarily need to be running, shut off all these any unnecessary daemons, things like that. Make sure you're in run level 3 unless you, for some reason, you need a GUI on this thing. If not, XAuth libraries will allow you to tunnel SSH and the GUI and stuff. So second step, BIOS tuning, which is, it's had more and more of an impact, especially as it encroaches on power management in the OS. Questions that you need to ask yourself, like whether hyperthreading or logical cores will give you any benefit, whether or not you need determinism or reduced jitter, which is where power management comes in, and then turbo. Are you highly threaded or not? If you're not highly threaded, then you'll get better performance likely with turbo because you can boost beyond the baseline top-end frequency. If you're highly threaded, all the CPUs are going to be running mostly full out anyway, so you probably won't get much of a benefit from turbo. So those are questions based on your workload, based on your development model that you might need to consider. And in fact, in 6.4, we have some tools to help surface more information than ever about what the CPUs are doing with regards to frequency and C states, which I'll go into all of that. So the last actual portion of this slide is more about interference from other parts of the operating system on a network layer. And most of these are around storage because it's slow. And what I've found, not only from dealing with customers over the years, but my own experimentation, is that things like running ext2 is out there being done because journaling has some extra code paths that you don't necessarily need if you don't care if your data is on disk or not. Sometimes the only thing that needs to get to disk, sometimes you don't care if it eventually gets to disk, whether it's logging or whatever. So maybe this is an option for you. Relatime is a new mount option that's a default in RHEL 6.4 that only updates mount times, access times when necessary. So it doesn't necessarily update it every time you check a file, where previous RHEL versions did, and there was much more of an impact. Sometimes Red Hat would advise you to mount with things like no A time or no dir time, much less of a problem in 6.4. So that's the default. You can cat proc mounts and double check. If you have carried FS tab over from a previous config management system, you might be overriding this, so double check that. Another thing you can do is slap a memory PCI storage in this thing, whether it's SSD or actual memory. What that can do is help reduce the round trip time to storage. So if you really do need to go to disk, it can kind of smooth that out a little bit. Instead of maybe taking a milli to come back, it can take significantly less time because the storage is just faster. Plus, it's local. Some customers run swapless because their application is designed in a way, and this is because swap can introduce these bumps in the road, right, in terms of jitter. But they run swapless because they don't care if the machine falls over. They want it to run and run and run and do its best, and then when it runs out of memory, bam, dead. Flip over to another node. That is a reality. People do it. And then finally, the most realistic, actually, probably out of these options I've left for last, which is if you do need to go to disk and you're using the page cache, right? Who uses a direct I/O for network-related applications? Okay. And if you're using page cache, the tunables in the kernel, like VM dirty star, whatever, the defaults are actually very sane for many, many workloads. What I'm recommending you experiment with here is to reduce them such that they write to disk more often, but less data gets transmitted, and thus the cycle is actually faster. So the same data gets to disk, it drips instead of floods and stops, that sort of thing. Okay, so how many times have you guys heard the word TuneD this week? Okay, should we change to log scale? What I concentrate on is the latency performance profile of the TuneD package. So all of our main feedback loop into the RHEL product is through this TuneD package. This comes from benchmarks, this comes from customer recommendations. Sometimes customers find stuff and we say, that is awesome, let's test that. And it gets rolled into this product. The latency performance profile, which you can enable TuneAtom profile latency performance, it does 4 things. Second column from the right is actually what it does. I/O scheduler deadline, CPU governor performance, transparent huge pages off, and actually going to lock the C states. As I mentioned earlier, if you have a low thread count, locking the C states will reduce your performance. So again, your mileage may vary. This is a baseline, something that we found to be, in fact, the C state lock actually helps with determinism. So you might get lower throughput, but let me tell you, I'll show you some graphs about how it will flatline some latency problems. So those are the 4 things that you get when you enable this profile. And you can back it out just as easily on the previous slide. You just TuneAtom profile default, and it unwinds all this stuff. Okay, so we've set the baseline. Systems, all the basic boxes are checked. Where do we go from here? This actually relates to NUMA in that, well, let me just phrase it this way. Locality of packets is all about avoiding the interprocessor link. And what that means is you need a number of things checked. You need all the NUMA stuff sorted out, and then you need the IRQs, and there's even a third step about PCI device locality to a particular socket. This is the ideal state. Can you ever get to this state? Maybe not, but what you want the common case to be in as close to this state as possible. And I'm saying stream from customer 1, whatever. That could be a web user. That could be a gateway inside an exchange, financial exchange, something like that. But when you have this one-to-one relationship, there's less interference from either going across links. There's increased cache sharing. Shaq mentioned TLB misses earlier. Really, all this network tuning is about staying inside that CPU cache as much as possible and avoiding memory and certainly avoiding disk. I'll actually work this slide from the bottom up. We have an excellent white paper on IRQ affinity tuning. It's on our portal. It deals with IRQ balance. It deals with manual affinity tuning. It deals with a combination of both of those, which is hairy and difficult to manage, but it is possible and fully documented. So that is actually a hyperlink. There's more links at the end of the deck, which will lead you. But if you go into access.redhat.com and you search for IRQ affinity, it will be one of the top results. Middle of the slide is actually the Tuna tool, which allows you to do manual affinity tuning. Certain NIC vendors ship things. I know Intel is one of them that ships these scripts that align these IRQs for you. I prefer Tuna only because it's NIC agnostic. That's some of the syntax there. What it does what it will do is take the P1 NIC, put its IRQs on socket 1, M is for move, and X is for spread. So it'll take the MSIX IRQ vectors, and it will align them in a one-to-one relationship and then loop back to the beginning if you have more IRQs than the socket has. Sometimes the ideal scenario, and you can do this most likely with module options, is to have the same number of IRQ vectors for your NIC as you do cores on the socket you want to run on. So let's say, for example, on a Sandy Bridge, you have 8 cores. You would change your module options to stand up 8 IRQs for that NIC. Starting back at the top of the slide, IRQ balance is very good in the common case, and in fact has improved in 6.4 to handle NUMA affinity already. If you have 6.4 and 6.4 user space, so that means that IRQ balance package has been updated in addition to the kernel, what you get is it keys off of certain values in sysfs and says, this PCI device is local to this CPU. I'm only going to use those CPUs for IRQ processing. So you're getting a lot of this stuff out of the box, automated by default with IRQ balance. I had mentioned some, oh, actually it's on there. Yeah, NUMA affinity for IRQs, great. The last thing is flow steering. It's fairly new, 6.2, I think we got software-based receive flow steering, which attempts to match the consumer with the CPU that's going to process the IRQ. And by consumer, I mean the application thread. And so it will dynamically move those IRQs around if the application gets moved around. It has some performance penalty because it's done in software. So there's been a move to handle flow steering in hardware. Again, and then it becomes vendor dependent, right? Who knows if you have the right NICs to do it. So that is coming in a future version of RHEL 6, and obviously upstream as well. How many folks are using NUMA Control right now? Not many. Task set? Just a very few. So what this command does is launch whatever command, and it binds it to socket 1 and memory bank 1. And all you need to do is prepend whatever command you want to run your application with that tuning, and that is it. That is your NUMA affinity. You could let NUMA-D handle it as well. That's how to do it manually. For the throughput, for the guys that are bound on throughput, NIC vendors have invented offloads. And in fact, folks from Red Hat have also worked on this. I created a brief chart here to let you know what certain offloads do, what they're intended for, what direction of traffic they impact, and what protocols that they impact as well. So this is more for actually kind of post-summit reference than anything. UFO I've seen implemented in test on about 1 or 2 NICs, so I wouldn't see that come up very often. But the rest of them certainly help throughput, and their goal is to aggregate packets such that there are fewer IRQs firing and reduce CPU usage accordingly. So instead of the host CPU doing it, the NIC does it, and thereby freeing up more cycles for your application to use. Whose application sets buffer sizes? Was your application taken from RHEL 5? When was it written?
Probably RHEL 4.
There's been improvements in the kernel that auto-size buffer, and when you set the buffer size in your application, set sock opt, you actually override that automatic tuning. And what you can do is create some head-of-line blocking problems in the buffer that actually adds latency. And so that's just something to be aware of. I've seen customers tune these things to insane values and get no benefit out of it. So what I wanted to do here is show you, in a controlled test environment, what the buffer depth looks like on a 10 gig TCP stream. It never gets above 4 megabytes. So if you've ever tweaked them to 64 or 128 meg buffers, it probably means you have a mismatched set of servers where you have a very slow receiver. And if that's the case, then there's a valid point to increasing the max of those. My point by mentioning it is to double check your source code. If you are setting it, it can actually hurt performance. And we found that in some of our acquisitions, actually, of companies that Red Hat has acquired where they were doing this and it was written so long ago, we ripped it out and performance went straight up. So double check. Who's using SRIOV? Anybody? Well, it's not that popular, and probably because it kills live migration. But I would say that the performance is incredible as compared to the bridge. So if you pass a device through, which is what SRIOV does, it allows you to take a single interface and carve it up into multiple virtual functions and pass those through into the guest. This slide here is network latency. It's an internal benchmark. The y-axis is latency in microseconds, and there's 4 groups of wow, that slide got messed up. I apologize. The key is wedged in the corner there. So the left-hand side is RHEL 6.4 tuned with the latency performance profile. The second column over is no latency performance profile, so the default. Third column is SRIOV, and fourth column is bridge. And the 4 columns each represent a different statistic, whether it's the average, the mean, 99.9%, or standard dev. And so what you can see here is a trend. Normally graphs going up and to the right are good if you're talking to the CFO of Red Hat or something like that. But this is actually, obviously up is lower is better. So what you have is, I mean, we're still talking microseconds, right? 165 microseconds for the 99.9 percentile on the bridge. So the bridge is a fully functional, performant technology in Linux. But here's what you can get with SRIOV. It's almost half, and further, a little bit of a penalty with virtualization there. And we're always working to tighten that up. Let's talk about power management for a minute. Who here has ever dealt with power management, configured their BIOS to disable power management? How many of y'all do that? Nice. Yeah, because it's a problem, man. It's definitely a problem. And you can see in this slide that there's an impact of it. This is actually the P states, which are CPU governors, and each column is a different governor. Power save, which means to lock you to the lowest frequency that the CPU reports. On demand is a burstable dynamic frequency variant. Performance is the highest end. And then I put the green in here to show you if you couple locking the frequency with locking the C states, you get even better performance. And that's the most significant drop towards the right. It's almost half when you lock the C states in addition to locking the frequencies. So you can use the CPU speed service to do this. You can do something weird in sysfs on your own. But by default, RHEL ships on demand, and it's a very respectable performance and power trade-off, really. I have another slide in here I'm going to get into in a minute that tells you what the actual business costs are to this. Yeah, you'll get better performance, but how hot does the data center get? So I had a slide before about P states. This is about C states. Processor voltages and sections of the processor that can get switched on and off on demand based on load usually. So when the tendency or the bias right now in Linux is to trend towards power savings and have a dynamic scaling performance when there's load. What you end up having, that dynamic scaling takes time to realize okay, I have load all of a sudden, I need to turn everything on and we need to go, go, go. That causes the jitter here. This is actually a Westmere system, again, an internal latency benchmark. The numbers across around the 200 mic line there towards the top of the graph are the C states that I've locked the processors into. So I ran this latency benchmark and I varied the C states and I just looked at graph the determinism over 15-second periods. And you can see as the processor gets more and more, it turns more and more of its feature set on, there's less and less jitter. And in fact, we're very, very tight on the standard dev side at C0. Questions so far? In the TuneD profile for latency performance, there's a Python script in there. Check it out.
So just a quick interrupt here, because Jeremy is sharing network latency, and quite frankly, some of the network loads are very lightly loaded, right? These loads are not consuming very much CPU, and so what the C-state governors are doing is indeed when they see idle, and even though he's running a benchmark on a load, it's saying, sorry, you don't have enough work to do. I'm going to put the CPU into coma and save power. And he's sharing, though, the fact to get out of that coma has a huge difference. And so really these options are just that. Before we take everyone's server in the data center and melt your data center through the floor because of power, which shouldn't happen, by the way. I do want to mention these are valid optimizations and is in the low latency, but it may not be the most, definitely is not the most green solution. But again, how do you extract the best latency? And Jeremy's sharing that with you.
Let me skip ahead a slide real quick to talk about the impact of this stuff. This is a watt meter attached to a server, 6.4 out of the box versus 6.4 locked at C0. That's how much extra power in terms of baseline is out of the box. The percent difference is how much how much power increase. So, and these are some internal benchmarks. So your mileage is definitely going to vary, but this is what the business guys are going to be interested in. So back to the previous slide. This is a tool that we began shipping in 6.4. It's been upstream for a while, and you can use it on any version of RHEL 6, but it's new in 6.4 that we are packaging it and shipping it in a RPM called CPU Power Utils. It's called TurboStat. Intel wrote it, so this is Intel's CPU specific. I apologize for the folks using AMD. But what we have here, if you look at the gray boxes, is I've got on the top-hand side of this graph, we've got the default scenario. This is out of the box on an idle system. The CPU favors power saving. It's going to get into the deepest C state, C7. You can see most of the processor time is spent in there. The second half of the slide, if I can draw your attention to the red arrow there, is after you enable the latency performance profile. It's going to give you that. And actually, 2 columns to the left is the clock frequency as well, so that's also locked. And what that'll do is help with jitter. Those are folks who are doing video and VoIP and financial stuff. Those are workloads that this is very relevant for. I did some benchmark effort with Security Technologies Analysis Center, STAC, last year and some into this year. And their harness exposed transparent huge pages jitter caused by transparent huge pages K-huge page D thread, which I have some data on in upcoming slides. Overall, it is a very sane default, an excellent win for many, many workloads. In 6.2, we added counters for it, so we've surfaced some more information, and Larry was telling me the other day that there's been even more patches, especially in 6.4, to reduce the impact of transparent huge pages. I should share that the test data that I have is on 6.3. So this is, can you guys read, can you see the red line there, and where the arrow's pointing? I hope you could. That's the outliers caused by THP. So in this application, I wasn't winning with THP at all. And so it was not a trade-off to decide to disable it. We're fairly tight standard dev. The y-axis is log microseconds. And you can see there, we're fairly tight. This jitter here is plus or minus 3 or 4 microseconds. And you can see there's a very, very periodic, and it's very clear that there's something going on there. So we started doing experimenting and tracing with things like perf and ftrace. And finally, we turned up transparent huge pages as part of the problem. So we whacked it, and it went away. We've got a very tight standard dev at the bottom. Now our average is actually 20 mics, as opposed to before it was like 100 plus. So your mileage may vary, as it is with anything in tuning. The answer is it depends. Okay, so new in 6.4, Tuna used to ship with merge. How many guys real-time kernel? Real-time kernel? All right. A couple guys experimenting with it maybe. I'm sure some folks have had some demos and stuff like that. But anyways, Tuna's written by the real-time guys at Red Hat, and we ship it in RHEL now. And if I can start your eyes off at bullet number 1, this is a Magna Cores, 2-socket Magna Core system, so 24 CPUs. Section 1 is representative of all the individual cores, how much load is on them. It's a fairly idle system. I ran a couple of test threads to, at least show you that there's something there. And they have tick boxes next to them. If you tick or untick those boxes and right-click, you can apply some affinity that way. Section 2, top right, is IRQs. In there, it enumerates all of the IRQs, their affinity, how many times they've fired, and what modules they're associated with. I have a screenshot in a minute on there's context menus for all of this stuff. So this is the home screen when you launch it. And again, if you install XAuth and you SSH in, you can get this over to your local workstation. You don't need a GUI for it, but it does have a CLI mode as well, which is what I'm most familiar with. The third section is the process tree. It has every process enumerated, every thread, lightweight process within the system, and again, context menus for tuning those processes. First half of this slide is the right-click menu. If you right-click on any old IRQ, you can apply affinity tuning this way. This is the same as echoing a value into proc IRQ, whatever number, SMP affinity. Does it through the GUI here. And second half of the slide allows you to do some tuning on processes that are already started up. You can change their scheduler. You can change their policy, their priority, and what CPUs they run on all through the GUI. Once you've settled on the right tuning, you can switch over to the command line and stick it in your, your init scripts, and and when the application gets started, it'll have all the proper tuning. And again, this is for hand tuning stuff, right? The common case is going to be automated stuff like IRQ balance and NUMA-D and flow steering, because your workload might be dynamic. Maybe you don't know what your workload is. Maybe you're a web company and you just launched a product and you have no idea if it's going to be a success or a failure. And suddenly it is a success. You want your system to dynamically tune as much as possible. So there's a trade-off for doing the manual stuff as well. Here's a slide of the command line stuff that you can do with Tuna. And I guess I've just highlighted some of the interesting stuff on this graph here. The thread affinity by default is FFF, means all CPUs. So whatever you've got, it's potentially going to run there based on what Larry was talking about earlier, where the scheduler might decide to balance load and move you around. Second half of the slide talks about how do you apply affinity. Like, you can do this with taskset as well, but Tuna has it as another option as well. And you can see the thread affinity after I've done -C2, the thread affinity jumps over to 2. So it'll only run on the second core. Another mode for IRQs, I briefly alluded to this earlier. Here's some of the output. So I said, okay, so in this case, I put it on socket 0, and upper Q is a query, so it'll spit out all of your IRQ affinity that's currently set. I've got a 1 MSI vector to core relationship there, and then just the module name on the right. For core and socket isolation, who's using or has heard of ISOL CPUs? ISOL CPUs, okay. Sets the init process inverted bit mask such that it only spawns children of init on whatever socket you didn't want to isolate, so the opposite socket. In this case, you have another alternative here with Tuna where you don't need to necessarily have stuff configured on the boot line and then reboot to actually apply the changes. There's an option here, -I for isolate, and what I've done here is shown you I've got just random old rsyslogd process can run on every core, apply the tuning, and then it updated and it's only able to run on socket 0. So I am running short on time, but I'm gonna try and speed up a little bit here. I mentioned earlier PCI bus topology. How do you get at that information? Here's a way to do it in SYS. By the way, I noticed a couple people taking pictures. There's tons of docs on our portal about this. And do they publish the presentations later? Yeah. So there you go. You'll have the deck as well. And you're more than welcome to reach out to us through support or the normal channels and all that. Anyway, here's a Mellanox NIC. And if you look in, so I fished this out of LSPCI. And I said, OK, this is my PCI address. And here's my local CPUs. Happen to be the odd numbers. I guess this must have been like a Westmere that I ran it on. And also, when you boot, it'll tell you what bus is connected to what NUMA node as well, right? But this is pretty hairy. It's all on the command line. We can do better. Here's a shot of us doing better. In 6.4, we have HW lock. Bill showed you a screenshot of this earlier. It was just one NUMA node. It also, in 6.4, can expose the PCI bus topology. So I know that this is on the top right. You can see this is NUMA node 1, and I can see on the bottom right, those are all my NICs and whatever PCI adapters hanging off that NUMA node. If you're not a fan of GUIs, you can do it on the command line as well. OK, who's heard of perf? Used perf? Uses perf every day? OK, so perf is an awesome tool of fishing hardware counters and kernel trace points data out. And people are always concerned about how lightweight is it. Well, whenever you're trying to measure this stuff, there's always a little bit of performance impact, but we're working on lightening that, and certainly this is as light as I've seen. Sometimes I really need as much data as I can, and it just slows down the app, but it is what it is. There's a trade-off there for analysis. So anyway, here's the wiki. We've rebased perf in 6.4 up to 3.6, so we've got, even though it's a 2.6.32 kernel, there's tons of new stuff, all the drivers rebased and this and that. But especially perf is what I'm interested in talking about right now. So it's up to 3.6, and we're going to keep it continually updated in the RHEL 6 lifetime. If you're familiar with the top, everyone's familiar with top. Perf has a top. If you do that, it'll spit out that. And what it tells you is how much CPU time is spent in what process and in what kernel function that's in. In this case, I was working on OpenShift, and I was scaling it vertically like a lot, huge, thousands and thousands of processes. And in the way OpenShift does their isolation, they use SE Linux. So what we have here is a kernel function that is standing on the CPU, and it is an SE Linux-related kernel function. So we found some tuning around that, and it's not a problem now. But that was a super easy way to find out why my CPUs were pegged all of a sudden. Perf top, 2 seconds, found me AV top search node, back to cscope or whatever to find the kernel source, and we actually published that on our on the customer portal as well, source code viewer. But found out what this guy was, and found some tuning to deal with that. Perf stat can spit out stuff like context switches. How often am I going in and out of the kernel? How many times have I changed CPUs? How many times have I faulted in new memory? So again, another option for analyzing your processes here. And there's tons of these options that are not covered in this deck. So there's some fairly good man pages and documentation on this. And so you can refer to man perf stat or something like that to get the details. Perf diff. OK, this is pretty cool. If you're doing different iterations of tuning, you run it once, tune, run it again, and do perf diff on the 2 output files. And what you end up with is a difference in performance on particular functions based on what, this delta here is whatever tuning I did. In this case, I just ran this process once, ran it again with task set, and saw a 15% performance increase by standing on one CPU. So, and this is just this is a derived benchmark, one of Bill's little doodad tools that just to develop a slide for you guys. But if you have a real load, this is the type of output that you can expect. So perf spits out these data files, right? Try to visualize them is a challenge, and perf diff is one of the ways to do it. There's another way. There's a tool called gprof2dot, or dot, which is in the GraphViz package. And what you can do is feed it a perf data recording file, and it will spit out this type of graph here. This is one subsection. This thing was like a mile long, because there's a ton of kernel functions involved in this. There's a little netperf test. The point is just to visualize that you've got these different kernel functions calling each other, and the lines have weights. So this is 28% of the time this kernel function is talking to this one. The command to do it is right there. OK, so I'm finishing up my slides now. The interesting and cool stuff in RHEL 6.4 of Tuna: latency performance profile, turbostat. HW lock has can hang the PCI bus off the side. PTP, if anyone's doing PTP, that's a tech preview in 6.4. And if you went to the NASA talk earlier today, they were passing IB into guests too, also I believe a tech preview in 6.4. Last slide. I mentioned kernel auto-tuning earlier. We auto-tune fairly well as compared to other operating systems. This is out of the box, tuned versus untuned. The untuned case is what I'm more concerned about because I don't want you guys to have to tune it. So we're doing pretty damn good, and then squeezing out a couple more percent as always with some manual tuning. Throughput on the left, latency on the right. This is a third party, as Shaq mentioned earlier, third-party benchmark. Don't know how to tune Windows. They did it. And I think we performed fairly well. Questions? Yeah. You want to make sure that your vhost net threads are pinned to the same socket that your vCPUs are pinned to. That's a big, big one. In fact, I blogged about it recently. And there's a Versh emulator pin is what you want to do, because the vhost net, so you do Versh vCPU pin your CPU threads, then Versh emulator pin, which takes the vhost threads and pins them on there as well. And that is a big, big improvement to VirtIO performance.
Any recommendations for virtual machine?
So the vhost thread pinning is one of them. So it's called Versh emulator pin, vhost being the actual emulator that you're pinning. And I think it was made generic because there'll be future versions like VirtIO SCSI we have, and we'll apply the same kind of tunings to there. So that's another one. But you want to make sure you're using vhostnet or SRIOV. The worst case scenario is if you're using an emulated driver like one of the Realtek NICs that we ship, or it's like a 100 meg NIC. You can expect very poor performance as compared to pass-through or SRIOV or even vhostnet.
Yeah, and I think that vhostnet is really get the VirtIO driver described if you're configuring things. It's
That's
the default technology in after Red Hat 6.1 for Red Hat, for KVM and Rev and things like that. So just don't leave it to an emulator mode and think, wow, the network performance on our virtual guest is, because it is actually horrible, right? It's emulating the device in software, and it's an order of magnitude, if not 2 orders of magnitude.
More like what kind of statistics? Is there a statistic tool for getting statistics out of virtual machines?
Repeat
In terms
the
of network
question.
performance, they would be the same as in a physical machine. I mean, the KVM guests would run all the normal tools.
Yes, repeat the question for the.
Oh, I apologize. He was asking for network statistics out of a KVM guest. Can't think of anything right now that you can't get inside the guest other than hardware counters. And I think they're working on a virtual PMU for that as well.
Right, and so we'll continue on questions. I'm going to switch gears now for the last quarter of the talk, and but actually, if there's any other quick question for Jeremy, okay, cool. So the last piece is pretty much disk I/O, and this topic kind of can extend. There's a number of other talks, so a database talk following this one. There's actually a Rev talk on performance tuning that's following this one, so you might have to choose. Or there's a number of Red Hat storage performance talks. I'm not going to get into that here because both there's one at on this little card here, if you saw them in the back or whatever, are all the, so that too is at 450. So you definitely got to make some choices for your next talk. If you want to, depending on what you want to see, Rev performance, database performance, or Red Hat storage performance. But you guys know we have elevators. One of the constant feedbacks that we've gotten recently for these different elevators is one, if you notice all our TuneD profiles, we changed the I/O elevator to Deadline, and we've been pushing to make that the default in Linux for a while, and it's happened. We finally are going to move that to the default, but it will happen in the next number release of RHEL as the default. So now you have to use the TuneD if you want Deadline. And really most modern storage takes advantage of it. If you have slower old spinning media, SATA, SAS drives, and that's your only storage, you may be better off completely fair queuing. And it was invented to basically be able to give you that even response time, not lock up the keyboard because you're doing disk I/O or whatever, more if graphics and things like that. So that is the default, but it's not completely. And then finally, we're seeing more and more no-op when you get to SSDs. So we may actually be modifying some of our TuneDs in the future to like enterprise storage or SSD storage. And the good news is we can add them to TuneD, or you can manually set these, and it's on the fly, no reboot required, all the devices, and we'll show you some of the scaling improvements that happen between RHEL 5 and 6, and some of the future stuff that's going to go on in 7. So just to show continuous improvement here, and this is kind of a comparison of file systems. So these are file systems we ship and support under RHEL 6. I don't know if you can see. We love a lot of bar graphs, as you can tell. But the bottom line is this was all done on the same fiber channel system. And then our release criteria is such that each of these bars is actually 14,000 data points of various I/O zone results under 14 categories. And we've got it down to a pretty good science of if we start regressing with our QE team and our kernel team, we're able to zero in on what type of file I/O we regress. And then those guys are always inventing cool new things, better file systems, better. And so this is RHEL 6.3 versus RHEL 6.4. Again, it's using a TuneD TuneD throughput performance profile. And then on the right-hand side, that's direct I/O. Actually, the QE matrix has grown to where they test memory map files, they test direct I/O, out of cache behavior. This is in cache. What's the other? F-Sync. And anyway, a huge matrix. And so really, when it comes to an application, here's another application performance slide for running the SAS mixed analytics workload. So it's not really a benchmark, but it's the thing the SAS CTO group said that this mimics the performance of SAS, on Windows and Linux for years, and Unix for years, and in fact, SAS has been the fastest moving application from Unix to Red Hat Linux, in the past 2 years. So, but clearly, you probably want, this is time, so lower is better. They do a lot of fairly large models, run them simultaneously, and XFS for high performance is now a clear leader for that. And so we do a lot of file system testing of applications, and in fact, you'll also see us use XFS with Red Hat storage with Gluster. XFS is the underlying storage choice we have, and we do have developers and maintenance for EXT 3 and 4. 4 has significant larger file system space and file system size more than space, and so it's the default today, EXT4. So in the future, we're considering, we're also running ButterFS, which is BTRFS, and that's in Fedora and upstream, and that's maturing quite nicely. I think it's in tech preview on Red Hat 6.4. So there's your tuning. Most of the time, we choose enterprise storage, and if I switch over to what enterprise storage does differently, well, it does do a disk read ahead. It bumps the value of each of the LUNs by a factor of 4 for the read ahead. When you get to SSDs, you may want to be even more aggressive than that, right? It sets the scheduler to deadline. The other thing it's doing, it turns off file system barrier. So the name enterprise storage means we hope you have, and in fact, the controller has to advertise itself to Red Hat Linux as being able to, I might have a cache on my controller, because like almost everything today does, even your laptops, right? Or I might have SSDs, et cetera, but they should be battery backed up, or they're responsible to flush submitted data. When we get I/O complete, and whether it's async I/O or whether it's standard buffered I/O, the file system folks got a little leery between Red Hat 5 and Red Hat 6. Too many people were running on a disk cache, and the disk cache didn't have a battery backup. They would lose their data, come to us saying, we want our data back. We're saying sorry. And the problem is it didn't always report it. So there's a mechanism to report yourself as a disk and a controller to whether you can support this capability or not. So independent of our disk manufacturers, the file system can add barriers. And there's a small cost. And initially that was maybe 5–6%. It's gotten lower, so we actually think that code we've optimized further. And so it may not be needed, hopefully not needed in the future RHEL. The other thing we mentioned before, and maybe Larry, you want to, well, I'll have you jump up in a few minutes when we talk about some of the tunables for the file systems. One thing to note, the Linux page cache. Linux is part of why Linux gets used and Unixes are used because they support a page cache that can do two things. You can do read-aheads that I mentioned before, and you can control them on a per-device basis. And then with writes, we can also aggregate writes together in the VFS layer and flush them to disk. And getting bigger block sizes is really useful. And the other thing we can do, though, is we keep that data in the page cache. We don't flush this until we believe that, it's more of a, because it's like a cache, if you wrote something there, you might come back to it and reuse it, and why would you need to pull it from disk again? So that reuse means that after about half an hour, half a day of doing some file I/O, if you do a VM stat, you probably see that your memory is down to like 5% of free memory. And so Larry and I are going to step you through why that is. It's, again, this page cache will use all available memory to various watermarks. And we can adjust that if it makes you happier to see more free memory. But the other thing we can do is adjust how frequently we flush the data out. And And so drop cache is a big hammer because it's going to drop either all the, the top is the page cache, the slab cache, and metadata, right, is in the slab cache. You can drop them, individually, or the big hammer number 3, you can do this dynamically. I did want to just revisit again the TuneD because we spent some time. I think the slide's a little out of order, but you see again the difference between running TuneD Enterprise Storage on various file systems, and it's a clear win on most of these I/O zone workloads that are using a geometric mean on 14,000 data points for each bar, and higher is better. And let's see, we have the left column is the in-cache values. Careful, the scales, I put the scales for the direct I/O, I put them down to the same, but in-cache means you're going to be running at memory speeds, so 4 gigabytes a second. When you get 4 gigabytes a second, unless you have a lot of SSDs, it's probably going to your memory. So on the right-hand side, 8 gig fiber, 800 megabytes a second is the peak. And so even out of cache, what we're able to do is we're able to run close to the disk speeds even when you're flushing data all the way, huge files that are outside the size of the memory on the system. As Jeremy mentioned, one of the things is to turn your BIOS to OS control. A lot of people said at least they're doing this. We'd love you, the customers, to tell your hardware vendors that some of that power saving they're doing, may or may not, is kind of costing you performance. And we hope to work with those vendors a little more, but I know everyone is trying to save power in the data center, but you kind of paid for these cores and these CPUs, and we're really more adamant that we let you use them, right? And not just keep them in high C states. Okay, so that's what's going on underneath and how to use it. And I'll just finish the same study that was going on, and so this is, again, the difference we gave. The team did their best to try to optimize a couple different windows. Those are in the blue and the light blue. We did, out of the box and tuned for the 2 Red Hat bars. So we did do ext4 and XFS. And these papers are available. Obviously, I think we, oops, am I going the right way? Sorry. Yeah, so this is the in-cache, and this is the out-of-cache. So, out of cache, the gain isn't quite as dramatic. Clearly, the in-cache, it's a significant improvement by Linux versus, this was Windows 2012, and both the NTFS and REFS is their newer file system. And so what's going on with tuning? So, Larry, you want to go through the?
Yeah, sure. So one of the other things that exists in RHEL 6 is a per device or LUN-based page flushing daemon. It actually, rather than having a global page flush daemon, there is one per file system, if you may. And so basically what it does is when you do file system reads and writes, it actually doesn't do anything to disk. It just modifies, it takes the page and the page cache, dirties it, and then there are two basic mechanisms of flushing dirty file system memory back to disk. The first one is just a % of memory. Once a certain % of memory is modified, it starts flicking these pages back to disk. As more of it gets modified and the system becomes more sort of compromised because there's more dirty memory, it actually starts more aggressively stopping the processes that are writing to disk, and then, stopping the processes that are modifying these page cache pages and forcing them to write back to disk to really start to throttle. And then the second major way that modified page cache pages get flushed back to disk is time-based. There is the old Unix update daemon. What it would do is take pages that were, say, 30 seconds old and sort of flick them back to disk. And we have the same basic background writing there. As pages are aged to, say, 30 seconds old, by default they will be written back to disk in, say, sort of by 5-second intervals by default. And this is all tunable in some of the parameters that you guys set in the
Yeah, so just a brief example. So this was an example. when the left-hand column is the number of simultaneous processes that are doing I/O to on the order of, I think there were, what does it say, how many LUNs? 480 LUNs on a system. And having a per LUN flush daemon, before we used to have like 8 daemons would all try to flush for the entire, all the I/O on your system. So, and that's a RHEL 5 before, okay? And so in RHEL 6, you go up to 1,000 LUNs, 500 LUNs, you know, it's going to be able to flush, you know, significantly faster. And then again, using a RHEL 6 TuneD, a paper on this was done in the past and is available. So we only have about 3 or 4 more minutes. We'll go through and then we'll accept final questions and nudge anybody next to you that might be asleep at this point.
So the TuneD profiles modify certain groups of parameters, reclaim ratios, write-back parameters, and read-ahead parameters. And basically the ones that are modified there, you can see sort of a picture here in terms of limiting the amount of memory that's dirty in the page cache. There is the background ratio, the dirty background ratio and the dirty ratio, and they are 10 and 20% by default. And as you can see, we basically do nothing with respect to writing modified pages back to disk in terms of percentages until we get to this dirty background ratio, which is 10% by default. Then we start asynchronously sort of flicking pages back to disk, and as we get higher and higher, we more aggressively do it to the point where we hit this dirty ratio, we stop the processes from running and aggressively write them back to disk. You can, if with enough processes on the system, you can still overwhelm it to the point where the page reclaim code, in a real extreme case, could be writing modified pages back to disk as well. You want to talk about the KVM stuff here?
Yeah, again, so real briefly, again, go to the next talk, you can see this, but TuneDs will help. I've been sharing the kind of the deltas, 10%, 20%. When you get into cloud environments or Red Hat storage, you can see some more aggressive read-aheads and tuning done. Again, it's in a profile. Just a quick intro to the gains, though. All of a sudden, instead of the 20%. So my team gets paid by Buffalo Wings for every percent that they can get. And so everybody wants to work on Red Hat storage because they're getting factors of 200 Buffalo Wings per sitting. So I'm going to stop there. We actually have some real interesting stuff, and anyone that can stump Larry, Bill, or Jeremy, because I'm not going to be included,